Alright, so now we need to talk about the effect of temperature on the reaction rate. Now generally, of course, you would probably guess that increasing temperature makes the reaction go faster, and you would be correct. It turns out that the rate constant, which we've been calling the rate constant the whole time, it's not actually constant. It's constant at a particular temperature. But if you change the temperature, you are going to change the constant. And this equation right here, the Arrhenius equation, is how the change in that rate constant is represented as it relates to temperature. So in this case, A is something called the frequency factor. The whole part on the right side there, that's called the exponential factor. And within that, EA is the activation energy, R is the gas constant, and T is temperature. So let's talk about each of these things. Activation energy is hopefully the one that you know about already. The activation energy is the energy it takes to get over that hump of the reaction. Okay, now depending on which direction you're coming from, if we were coming in the reverse direction here, then the activation energy would have been this whole thing. But because of the fact that we're going forward, it's only the top part there. That is also called the energy barrier. It's the amount of energy it takes to get the reactants to turn into products. The frequency factor is A, remember, and basically the frequency factor is just the number of times we try to get over the activation barrier. So the number of successful or correctly oriented collisions, it's the attempts at getting over the activation barrier. The exponential factor is the percentage that actually make it. So you're thinking about, well, consider your free throws. Your free throw percentage is like the exponential factor. The number of free throws you take is like the frequency factor. If you multiply the number you take by the decimal form, which is your free throw percentage, you should get how many you make. Same thing is true here. The frequency factor is the number of attempts at getting over the activation barrier. The exponential factor is the percentage that actually make it. So when you multiply those together, you should get the number that do make it over. So what this means is a large activation energy and a low temperature make it really hard for the reaction to proceed. However, if you have a high temperature or a low activation energy, more will get over, and so that's why raising the temperature typically allows the reaction to proceed more quickly. So all of these attempts at getting over exponential factor is the percentage, and temperature is going to help get over. Yeah, we talked about all those. So let's think back to the collision model again. There's something very important that I did not discuss just now, and that is orientation. And orientation actually goes into making the frequency factor. So the frequency factor is actually made up of two other variables. One's called the orientation factor, the other is called the collision frequency. And just like the frequency factor is the number of attempts at getting over the activation barrier, the collision frequency is just the number of collisions. Now obviously not every collision is going to be a good attempt at getting over the activation barrier because they're not going to be oriented correctly, so we're just not even considering that an attempt. In order to be a good attempt at getting over the activation barrier, you have to have the correct orientation, or else the reaction couldn't happen anyways. So the collision frequency is the number of collisions. The orientation factor is the percentage that have the correct orientation. So once again, if you take the number times the percentage that have the correct orientation, what you get is the number of collisions that do have that correct orientation and therefore have an attempt at getting over the activation barrier. So just kind of a visual here. No matter what happens, if you have incorrect orientation, you can't have a successful reaction. The only way you can have one is if you have correct orientation. But then, once you have correct orientation, remember you still have to get over the activation barrier, so there's still two options. Even with the correct orientation, this one doesn't have enough energy. This one has correct orientation, incorrect energy, and so this one will react. Some have a orientation factor, an orientation factor greater than 1, it basically just involves an exchange of electrons. Sort of the potassium here would send an electron out like a harpoon, and then you have a charge difference between them. So the bromine would now have a negative charge, the potassium would have a positive, and they'd come together. So it is possible. You don't need to worry about it too much. I just tell you in case that ever does come up and you're wondering about it. All right, I think that's where we leave off for this one.